below. And then we've got 2 activities, and we'll split you into 2 groups. One group is going to stay here and play with the slinky seismometers. It's an example sitting over there on the table, like one that's wearing a crow. And the other group's going to go outside and, with the help of the U of O students here, actually do what seismologists call active source refraction. I'm not really a seismologist. Refraction experiments. And with that, swinging the hammer, there's some geophones out. You'll be able to look at the projection of what's on the computer, and hopefully we'll see what the site looks like. Maybe we'll see bedrock, maybe not. We'll try to, we haven't done it. Maybe it's a mystery at this point. So, why don't you go ahead and start off, John?
Okay, and if it's too far in the back, there are seats up here you can have. And if you have any questions as I'm doing things, please ask them. We're here to help you, and I really don't have an agenda except to try and help out a little bit. So the things I'd like to cover today, what Dean would like to cover, is improving earthquake awareness in the Pacific Northwest and how we can engage K through 12 in doing that. So Dean and I are both involved in a large onshore-offshore seismic experiment to take a look at earthquakes in the Pacific Northwest. And part of any National Science Foundation funded experiment is we engage in education and outreach. And it's increasingly interesting and useful for us to do that. And so we've come up with some ideas today that we're pursuing and we've started, and feedback would be useful. So I'll say a little bit about that. Then I think Dean's going to do the observing seismic waves part, and I'll come back and say a little bit about site response, and you'll understand what I mean by that in a few moments. So the first thing is that we live in an area that does have severe earthquake hazards. There have been large magnitude 9s in the past, and while I think coastal communities are well aware of that, here in the valley, I think my impression is earthquake awareness is not that high on our list, and we'd like to change that. There are different ways we can try and do that, and one of those is simply through educational efforts. And one of the things that Dean and I have been doing lately, and you'll get to see, is installing slinky seismometers in schools. We have one now in the Crow Middle and High School. And these slinky seismometers, you'll work through several stations and see the simple principles that let them work. But what's fascinating about them is you can record global earthquakes. So in your classroom, you can record earthquakes, the recent Iranian earthquake or the Kurils earthquake. With a little bit of education, students can both build these, see earthquakes that occur globally, and probably use that for anything from understanding earthquakes and tectonics to just geography, because earthquakes occur all over the globe. The other thing that we're trying to do is what we call seismometers at schools, or SAS or SAS, which is actually putting real seismometers in the basement of schools to record site response. And I'll explain that a little bit later, but knowing how each individual site responds to an earthquake can inform you of what sort of rebuilding you might need before the earthquake happens. So a big discussion here in this neighborhood, I have 2 kids in Edison, is that this school is either going to be torn down or rebuilt. Well, if it's going to be either one of those, the thing that replaces it has to be up to earthquake standards. So by going to each site, we can evaluate that. And our goal is to gather hard data, but also involve the schools in gathering that data. And I think it's something where high school students could participate with us and find out if their site, does Sheldon shake more than South Eugene, have a little competition, who's the best, who's the worst, and then actually send these students out into the 4J districts or local communities and advocate for this sort of future. And then the third thing we're going to do today is we've set up an active source seismic refraction experiment on the playground here. And this is something that my field geophysics class is doing as part of their undergraduate and graduate education. And we actually have real-world applications of this. And we'll talk about Highway 20, which if you're from Oregon, you should know a little bit about Highway 20. If they had thought a little bit beforehand, they might not have wasted $100 million. And there's some debate about how many of these landslides are triggered by earthquakes, and that's something that as scientists we're interested in evaluating. So we're doing experiments out there, and I know these experiments aren't that hard, and junior high and high school students can do it. And I've taken my elementary school kids to Newberry and done seismometer installations there, so it's something that I think can engage everybody. So I hope most people are familiar that we live on a subduction zone that's capable of generating earthquakes. How many people are familiar with the slip of earthquakes? Right, so it raises up and goes down. And I'll say a little bit more about that. The last earthquake that we had here that was a magnitude 9, do you know the year?
Yes, 1700,
1700.
January 20th.
All right, fantastic. And,
26th.
what's
Does it say it up there?
9 a.m. Okay, so that's great. I'm really glad you know that. So right now the experiment that's ongoing, it's something that's, we've had our first year's effort, is actually deploying seismometers from roughly Cape Mendocino up to Vancouver. Of course, there are many land-based stations, but what's unique about this is we have seismometers extending all the way across the Juan de Fuca Plate and up into shallow water, and that's the first time for our community because shallow water instruments get dredged up by fishermen. We've avoided it. So we've tried to build instruments they can't dredge up, and 80% of the Earth's subduction zones are offshore, and so we really need to go offshore to see them, and it's a new chance to try and collect some useful data. So this is two photos, a little bit maybe difficult for you to see. The first is just the drowned forest or the ghost forest that we have along the Oregon coast because in the cycle where it's stuck, the land raises up out of the water, and when a large magnitude earthquake occurs, it slips and it subsides, and it takes all those roots that were in fresh water and puts them in brackish water, and they all die synchronously up and down the coast. There's actually some other really fascinating information. This is Brian Atwater and others, is that you can see old Indian hearths that they had along the beach and charcoal and other refuse from where they were living. And then a large earthquake occurred. The tsunami came through and buried that. And so in cross sections on the coastal area, you can see turbidites, or tsunami deposits in this case, not turbidites, but tsunami deposits overlying ancient hearths and coal, or charcoal. So I think, I came here in the early 1990s, and Oregon at that time really had not very much awareness that there was earthquakes. And I think the scientific community, and obviously all of you as well, now know that we have these events, and so that's great. All right, a little bit about the Seismometer at Schools program. The Slinky seismometers, you're going to see those. We have one in Crow that is now broadcasting data to the world. It took us a little effort to do that, but we're learning how to do it. We're going to put one here in Edison Elementary. We gave a demonstration yesterday as part of Ocean Week. The kids got really excited to see how seismometers work, and hopefully we'll have one running up in the principal's office so the kids can come by each week. Roughly there's a magnitude 6 or greater once per week, and so that gives you an opportunity to see earthquake records from those. This is something, the Slinky seismometer is relatively inexpensive, so it's something that we hope to propagate through many schools in the area and actually have a little network of these that people can have as part of their educational toolkit. I think some of the students at Crow are interested in building one of these. I know I've had a couple people at the university come up and ask me for the plans. You can Google this. They're built by Boise State University, so if you Google Slinky seismometer, Boise State University, they have all the plans there, an actual website of a 5th grader who built one. So, not hard to do. The real seismometer has already said a little bit about that, and our hope is to try and get the workflow set up enough that we can have high school students come collect the data, install the seismometers, and do some of the basic analysis. And I think that's an excellent goal, not just from an earthquake preparedness point of view, but one of the things we're interested in doing as scientists is to have younger people learn how to collect data and simply how to graph it, right? I think that's an important thing of collecting it yourself and making a graph and building up those skills. So one last thing I think, is everyone knows about Highway 20. Our class is going out there in a few weeks, and we're going to do a very similar experiment to what's out here in the playground. We're going to do it on a slightly larger scale, and we're going to try and measure the thickness of that landslide that has caused problems for the construction. You can see evidence of these landslides. Oh, this is too hard to see. But if you ever go in the Coast Ranges, you'll see dissected topography, sort of pyramidal shaped, eroded by rivers. But occasionally you'll see these areas that instead of being dissected like this, they'll be this sort of hummocky terrains. And these are deep-seated landslides. There are literally thousands of them in the Coast Range. Triangle Lake was formed by a landslide as well. And so these features, the geomorphologists don't know how thick they are, what their basal structure is. And what we're trying to do as part of this class is each year go to a different landslide, collect a data set, and then over a period of 5 to 6 years have enough measurements to say something hopefully useful about that. And again, I think, we're teething ourselves trying to figure out how to do this, but after a year or two, I think it's something that junior high and high school students could easily spend a day in the field with us and see how seismologists collect data. All right, we're going to have a demonstration of that on the playground, and the big announcement is we have some ice cream for you as well at the end of the day. So if you swing the sledgehammer hard enough, it's like a circus. You can get an ice cream. All right.
Okay, I'm going to unplug and replug because I'm in a different computer here. Hopefully it's dead. So I kind of wanted to introduce, introduce seismic waves using some Vernier kit, which you guys have used some of today. So one thing that's interesting to do is to try to actually look at the speed of sound, all right, because seismic waves are sound waves in the earth. So I think what you can do is a really easy experiment where you look at the speed of sound in air, and then we'll segue and look at the speed of sound in a table, which is not quite the earth, but close enough. So what I did was I took 2 of these Vernier stick microphones. All right, they're pretty cheap. We'll probably buy some, right? And hooked them up to a LabQuest, and then I put that onto the computer, and then it's not projecting. Let me
You need to
wake it
plug
up.
in.
It's not.
You didn't
Almost not.
click it in.
Oh, there we go. That's the old problem. Yeah, what is this? Go away. There we go. I can tell I'm projecting because it looks so crappy. All right, so now the way I did this was I actually plugged the microphones into the LabQuest, and then I plugged that into the computer, and then I fired up Logger Pro. And Logger Pro said, "Oh, you've got microphones," and it more or less set up approximately what I needed for in terms of data. But there's one trick to this. Right? Sound waves are fairly high frequency, right? Anywhere from 60 to 20 kilohertz or so, and so they go by fast, in so many words. And so in order to sample and look at sound waves, you've got to sample fast, right? So Vernier will kind of assume that because you're hooked up to microphones and you want to listen to sound. So what we can do is you can click on this little area here. This is data collection. This is where I usually live at the UFO. And notice it's taking it at 10,000 samples per second. And it's only going to take 0.03 seconds worth of data. All right, so let's just do that. I'm going to turn triggering off for now because I had it on. So I'm going to take some data. I'm going to go up. There, done. 0.03 seconds, done. All right, so that's not going to suffice, right? Because I want to, I don't want to look at 0.03 seconds. I kind of want to keep looking at sound waves. So let's say if we wanted to just simply use this thing as sort of an oscilloscope with a microphone hooked up to it. We go into collection, and we'd say repeat, right there. Say done, and now when I say go, it'll just keep going until I quit. So then I can come over and grab a microphone and go, you can see it, right? You don't have to hit the right 0.03 seconds worth to get it. In other words, it's just continuously cycling through. Okay, so that's kind of a little bit more about using microphones. But then what we want to do with this, and shut it down here, is we actually want to get this to trigger. Okay, and that means we're going to make a clap close to this microphone here, and we're going to see how long it takes for that clap signal to hit this microphone, and also how long it takes before it gets to the second microphone 1 meter away. Okay? And so in order to do that, I need to trigger, because I'm not fast enough to hit the right 0.03 seconds to get the clap, and it's like, oh my God, I missed it, So I'm going to go ahead and set this up for triggering. Notice there's a triggering tab. You can tell it trigger on a sensor value. And I've already set this up. The average sound value that I saw from these graphs here was about 2.5. So I'm going to say when the sound value goes above 2.8, I want you to start taking data. That's my clap. I just clap, it's coming in. So does that make sense? You're basically saying start when you hear a noise.
Yeah.
All right? And you can control that. You can play around with this 2.8 if you've got a noisy classroom and you got 5 groups of kids clapping and they're triggering each other's and that kind of thing. You could jack it up a little higher. You could play around. You could get your kids to play around with it if you wanted students. But the other thing is it's even smarter than that, because I can tell it to take 40 samples before the trigger. So it's sitting there and sort of continuously watching what's going on in the microphone, and it sees the trigger and it remembers the 40 seconds before the trigger. The 40 samples, I'm sorry. I can actually sample up to 126 samples before the trigger. All right, so I found a good value. Huh?
Each
Sorry?
sample is still 0.03, so 40
Each
samples.
sample is, you notice that it's sampling at 10 kilohertz, so each sample is what, 10 to the minus 4th seconds apart, right? So it's taking that, that's how far. So 40 times that would give you the time interval before, and it's a pretty short time interval, as you can expect. And you're welcome to play with this number. I found 40 to be a pretty good number. What I found is if I put too many samples before, then it actually shows me most of before and not much of the signal itself. That's the challenge. So done, okay? And we're pretty much ready to do our experiment at this point. And so somebody want to be my clapper? To be right where Shannon is. Sorry, Shannon. Okay, so there's no problem. See, I'm gonna hit go, and watch what happens. Waiting for trigger. It's waiting for the trigger. There we go. Beautiful. So that, and then now here's the next trick. Shut it off after this, because if I trigger it again, it'll overwrite that beautiful data. So just hit the red button, stop.
Doesn't this need to be exactly at the beginning and end?
Well, it's pretty darn close, though.
Now the cool thing I think about this is they look like seismic signals, right?
Yeah.
I mean, they kind of look like if you looked at seismic signals, they kind of look like that. So it's kind of nice because the students would get used to looking at seismic signals from sound. And what I can do is I can go under this Analyze, Examine, right? Analyze, Examine. And then it just gives me this little cross here and it gives me the values. And I can say, oh, right about there, that's when the clap first hit the red close microphone. So what's the time? 0.0002 seconds, minus, all right? Then I can go over here and I can say right about there is where it hit the blue microphone. And that is 0.0027 seconds. So if I took 0.0027 minus 0.0002 seconds, I get 0.0029 seconds. That's the time that it took for the clap to travel 1 meter between those two microphones. So all I gotta do is fire up the calculator here and just take 1 divided by that number. And it's telling me that the speed of sound in air in here is about 370 meters per second. That's not a bad number. It's about 340. So, that's pretty good, okay? And you could be more careful than I was. So I wanted to just go back briefly here. Now when I pick these guys, notice that there's this little dip right there, and then it kind of comes up, and then it goes high again. And on the blue signal, there's a little dip right there, and then it comes up and it goes high. I'm looking for that pattern to repeat from one signal to the next. And that's kind of what I'm using. I'm trying to pick the same place in that pattern. All right. And this is the way you would pick seismic records as well. You'd be kind of looking for it. It's not a particular pattern. You might look for the same pattern between one station and the next, but it might be slightly different for other reasons. But, you know, trying to get started on that. So who thinks, take a minute and tell me what you think the speed of sound in the table is going to be compared to in the air. Why don't you confer with your neighbor and come up with a guess? Is it going to be greater, the same, or less? When I measure the speed of sound in the table as opposed to air.
Could it be more resistant?
Notice the high-tech microphone stands?
What do you think?
This is not the best table, but it's just over a meter long. Do kind of an angle to it.
Or is it